I would like to talk a little bit about some of the synthetic data workflows that I've been uh, more or less using through my research in the past. Now it's been two and a half, almost 3 years. With I would give some examples, some hands-on stuff that I found quite interesting and useful, as well as some examples from my own research. Hopefully it's going to be maybe it's going to be interesting to a wider audience. But yeah, just one or two more things. I think Dean more or less gave a really nice overview of what I'm doing. So yes, I finished my PhD in Aalborg University as well in computer vision, 3D reconstruction, and point cloud analysis. So already from there, I had a kind of a nice mixed background where I had to use some computer vision, some deep learning, some computer graphics, had to use some computational photography to get to kind of mix it together and get the most out of it. I've since then worked quite a lot with anomaly detection and semantic segmentation for mostly indoor scenes, but sometimes outdoor. The inverse, sorry. So mostly outdoor scenes, but sometimes indoor. And currently I'm working as an assistant professor focused on synthetic data generation and also combining computer graphics, XR with some modern, more buzzword stuff like LLM, like generative models and so on. But today I would like to talk to you about these three building blocks that I kind of like to separate the synthetic data generation. And of course, this is only my kind of outlook on the subject. And I imagine that there is also maybe among the audience, there's people that have worked with synthetic data in one way or the other, and they might see some of the stuff, or they might have used and seen stuff that I'm not going to present here, but hopefully it's going to be interesting. First, we'll start with kind of a basic. The first building block is the capturing the real world, where I would like to talk a little bit about some of the concepts and software solutions that I use to capture objects and environments, to use them as environments like digital twins. Then I'll talk a little bit about generating assets and variations that we can populate our synthetic environments. And finally, put it all together with some stuff that would be useful with game engines that we can use for, I'm sorry, something, I don't know if it's from me. Okay. Kind of putting it all together. And we start by capturing the real world. So my background from my PhD and previous work is a lot in structure from motion and photogrammetry. And at the time, I was using it for reconstructing 3D scenes and especially reconstructing surfaces for surface inspection. And the good thing about structure from motion is that it's a very mature, reliable, and scalable solution. So this has been, we joke with my colleagues that it's a more or less finished problem. Of course, there's never a finished problem, but we kind of say it like that because we have so many open source and paid solutions that can give us from a couple of images, doesn't matter if it's from a DSLR high resolution camera or from a phone camera, we can get really nice 3D reconstructions with colors, with very small details. And of course, a lot of the algorithmic details from structure from motion are actually some of the stuff that goes into NURBS and Gaussian splatting. I'm not going to be talking too much about them. I'm just going to mention them because my current research is a little bit there, but it's not mature enough to kind of give a good overview. And the field is moving so fast that it's by the point would be already too old what I'm going to be talking about here. But from structure from motion, I would say that from my experience, I've worked with open source solutions and with commercial with some free licenses. And I would say that if you want to reconstruct larger, let's say larger areas like rooms or smaller objects like, let's say you want to reconstruct some bottles for inspection or some, let's say some items for, let's say if you're in the medical or automotive industry, that's quite useful because for that you just need a camera. And in my experience, Meshroom as an open source 3D reconstruction software is very powerful, it's very useful. From the semi-commercial, but with a free license, is Reality Capture, I would say, and Metashape. Reality Capture currently is under the Epic umbrella of items. So it's quite nice if you are working with Unreal, because there you can have that directly in your workflow. And of course, we have Micmac and Colmup that are actually quite a lot used together as starting points for NURBS and Gaussian splatting to get camera positions. But for the people that don't know what structure from motion is, just a very quick overview. Let's say we have a number of images. Here we have this little angel statue, and we have images from different perspectives, from different points of view. Then we can, what we want to do is capture and create this kind of a 3D model of the statue as we are seeing it in the images. And how it's done? Well, we start by capturing, getting the captured images and use quite a lot of these old school computer vision algorithms for feature detection, feature matching, and outlier removal. So here, for example, we can see the angel statue from two different perspectives. And here we can see this is an output from one of the programs. This is from Metashape, where the blue dots on the angel are features that have been detected between the two images and have been successfully matched. All the other white ones are outliers that would be removed. So these we don't care about. Once we have these matches between the different viewpoints, well, it's quite easy to use them to calculate the camera positions, because for a lot of structure from motion and photogrammetry, we either know the intrinsic camera parameters like focal length, like resolution, like and we also know, or we can easily calculate the extrinsic one. So what is the position, what is the rotation of the camera at that point? Once we have these positions, then it's quite straightforward to calculate and reproject a very sparse point cloud. So here, I don't know if you can see, but we have a point cloud of the angel statue, which is very sparse. So if I zoom it here, you would see that there's a lot of gaps. We only get the most specific feature points that we have reprojected back into 3D space from all of the cameras. But from there, it's straightforward that we can densify the point cloud. And here we can see that we get from a very sparse one to a more dense one, with some added noise from the background and from, for example, the place where the object was put. Then we can, once we have this dense point cloud, we can remove the outliers again, and we can create a mesh out of it. And meshifying it can be done with all the kind of really, at this point, old school meshing algorithms like rolling ball or Poisson for reconstructing the mesh. And the added benefit is because we have these images from all directions of the statue, then it's quite easy to reproject the images and get a very high resolution texture. So this is one of the things why photogrammetry and structure for motion is really powerful for these digital twins, because then you get even more detail that maybe the 3D model lacks by getting the texture. And of course, from there, we can have the more modern solutions like neural radiance fields, where we use a neural network, we train it, we overfit a neural network on a specific set of images to generate a neural radiance field, which represents a 3D object. With this, we can create powerful novel views from a 3D object, and we can create very highly detailed representation, where we can capture very small structures, let's say leaves and branches on a tree. We can capture, like, for example, hairs on a stuffed animal here. The only problem, at least to some extent, with some neural radiance fields, now we have quite new research from 2024 that tries to address this. It has problems with large input images, and it requires quite a lot of computation time. But the good thing about it is that it's multi-platform currently. We are getting more and more research about editing them. So we can, for example, cut off parts that we don't need. So we can create standalone objects or standalone areas. And of course, we also have the 3D Gaussian splatting that is even more powerful because of the less amount of training time and currently even smaller sizes. And that's all nice. We have, let's say, from the photogrammetry and structure for motion, we get a very high resolution, very, very detailed 3D model of that statue. But that model can be, let's say, 1 million, 10 million, 15 million vertices and faces, which we cannot use for, let's say, we cannot put it easily in a game engine to create our synthetic data. Or we can, but it's going to be very laggy. It's not going to be very optimized. So one of the next things that I like to do is to retopologize the mesh, meaning that we can go from something that's very high resolution, very detailed, to something that is much more friendly to engines, let's say, like Unity, like Unreal, like Godot, that we can go from 1 million faces to something like 10,000, 20,000 faces without losing their overall shape. And then, which would be very nice. And for that, I use a lot of times Instant Mesh, the program called Instant Mesh. You can do the same thing with, let's say, Blender, Maya, 3ds Max, but the Instant Mesh, the good thing about it is that it's standalone, it's free, and you cannot beat that. And it's quite powerful for something that's around 20 megabytes in size. And once we have that retopologized 3D object, and we have the really high resolution texture, albedo textures, one of the next things that I like to do is to calculate and generate some of the other textures that I might need when I'm creating the digital twin of the object. So that might be normal, bump maps, displacements, smoothness maps, metallicness, so reflectivity maps. And one way that I do it is using Materialize. Again, and this is something that you would see a lot in this presentation, is that a lot of these applications are open source and they're free. So Materialize is very nice. It's you give it, let's say, just an albedo, and then by tweaking parameters in a couple of menus. I mean, the menus can be a little bit better created. It's you could straight away see that it's made by a programmer and not a designer. But it's very useful to very fast and very easily create important textures like normal maps and displacement maps and metallicness by tweaking a bunch of parameters until whatever you see here is to your liking. And then you can export them. And finally, let's say we have our nice angel statue, and we have the texture of it, the albedo texture. But the problem is that even if I try to capture all the images in nice lighting environment where there's no harsh shadows, no glints on the object if it was smooth, sometimes we can get some lighting that is baked into the texture. And a lot of times we don't want to have that, because if we want to put it, let's say, in a digital twin environment, in an engine where we want to create synthetic data, we want to put the lighting in places that we want. Let's say that I've captured the angel statue in an indoor environment, but I want to put it in an outdoor environment where the sun is at, let's say, 10 o'clock in the morning. Then those shadows that are baked, we don't want. A nice software from Agisoft, the same people that made Metashape, and it's free again, is the D-Lighter. And that software is quite simple, but very powerful. So you can start with something like this, where we have an object that has some kind of burned in shadows here that we can see. We can specify, okay, these parts in yellow, they are in the sun. And these parts in blue, they're in shadow. Then what the software tries to do is to remove the shadow parts and try to approximate the color based on the parts where there is sun. And what we end up here is something like this. Here, it doesn't look nice, but this is exactly what we need. We want a 3D model where the texture is free of any shadows, self-shadowing, shadows from some other objects, and so on. Because now, if I put a light, let's say a directional light pointing a specific position of our object, then we're only going to get those synthetic shadows that we want. And with that, I'm going to the next part, and that is the generating asset variations. Because up to this point, we've been talking about how to get something from the real world and digitize it and put it in our, let's say, scene for our synthetic data. But maybe we want to add some assets together with it. May that be, let's say, digital humans, may that be some kind of HDR maps, may that be some backgrounds, some texture, some objects that we have not digitized ourselves, but we want to still have enough variation so our synthetic data for, let's say, training a deep learning model or a computer vision model would have enough variation so we don't overfit it. And the first one is some of the applications that I use for human model animation and even more human, so kind of variations in also the visuals of the humans. These three are quite useful pieces of software, or some of them are also online. One of the ones that I use a lot, and most probably a lot of you that have done anything with game development or synthetic data have also used this Mixamo. They're part of Adobe. And what you get here is you get a nice database of pre-made animations that you can use directly in engines like Unreal or Unity or Godot. Straight away, we have everything that's rigged. We have a lot of animations that some can animations, let's say like people walking, jumping, falling down, and I'll show you that later, some of the examples of that. And then we also have AccuRig. AccuRig is when we want to create something additionally. Let's say we got something, the animation that a person is jumping, but we don't like how the hands of the person are moving in the jump. Then in AccuRig, we can actually change that a little bit, make it so the jump animation is a little bit more smooth. And finally, Flask. This is a software that I personally use. Nowadays, there's a ton of these software solutions where you can capture, let's say, a person doing an action, and then run it through the software, and we can get the animation of the person just. So, for example, here we have a woman and a man that are dancing, and then we can directly get just the dancing animation. AccuRig is paid, but the good thing is that you can get up to 20 seconds of animation for free. And I've seen, at least from personal experience, that 20 seconds is more than enough for a lot of my uses in synthetic animation. The next one is Sloyd. This is a nice piece of software that I use when I need to have some objects in the background that need to be just varied enough so we don't get the same overfitting on the same type of visuals. Sloyd is very nice because you can get variations of simple objects, like, for example, here, TVs. It's by just randomizing different parts of it. So for a TV, it will be the frame, the stand, the size of it, and so on, which is quite nice to create, let's say, 10 or 15 different versions of the TV, where we can put it in our different variations of a room that we are creating, for example. And this goes hand in hand with Polycam, material generator. I use this when I want to have variations for outdoors environments, especially. This is really nice because they use a pre-trained generative model. I think they're using a version of Stable Diffusion, so a diffuser model that we can generate different variations of, let's say, brick walls, or we can create different pavements, wooden flooring, and so on, which can just make our visuals a little bit more, a little bit nicer. And the good thing is, again, that we get both albedo, but also normal maps, roughness maps, and so on. And this goes hand in hand with Many Worlds' Rosebud's skyboxes. Those by no means are very good. I've used them only in one project, and I had to tweak a lot to get skyboxes that are consistent enough. But for simpler versions of, let's say, different types of cloudy skies, sunny skies, and so on, they give a very nice variation. Of course, you can go very crazy with them, make some sci-fi stuff, underwater stuff, but those have a lot of artifacts, and I would advise against it. But for normal skyboxes, they're very nice. Monster Mesh is something that my students are using currently for one of their projects, for making backgrounds, because they're using it for creating 3D animal enclosure videos, where we want to have some animals in the background far away that we might not care that they're very high resolution, but we still want them to be able to move around and be 3D enough. So Monster Mesh is quite simple, quite quick and dirty. You can make some pseudo 3D models that would be very nice in the background. And you can very easily extract a very basic 3D model directly from them and then repurpose it in Blender by, for example, cutting into smaller pieces. For example, here, the elephant's ears and trunk and legs are additionally cut so you can animate them. MetaHuman, I mean, that's something, again, from the Epic toolkit, where we can create a lot of hyper-realistic faces. Currently, I have, no, not currently. Last semester, I had a group that was trying to use MetaHuman uh, extracted humans for facial detection training. So trying to train only on synthetic data so we can be more GDPR compliant. Results were kind of mixed, but the good thing about it is it's very easy to create a lot of variations, very easily change the age, the gender, the ethnicity, and so on, that we can create a lot of variations so we can have models that are not just trained on with a bias of specific, let's say, skin color and so on, but we can have a more inclusive model. And finally, putting it all together. And here I would want to talk about the game engines that I've been using to get all of these generative assets and captured for the real world assets and put it together. And after that, I will give some real world examples from some of my research. But before that, Unity. So for my first education and then earlier research kind of practice, I've been more of a Unity person than an Unreal or Godot or NVIDIA person. But so I mostly use Unity to build my synthetic environments. And with that, I use either the computer vision, or now known as perception, part of Unity, or the older one that was called computer vision tools. The good thing about that is that if we have something like, let's see, we have an environment here with the two cars. In Unity, we can set up and say, okay, this is, let's say, a BMW car, and this is a Kia, and all cars that are, we can have all cars already segmented by category and saying, okay, all the cars are going to be blue, all the trees are going to be green, and so on. So we get perfect segmentations. And we can go even deeper and say, okay, I want the IDs of them. I want this specific BMW number 1 to be ID 1, and then another, if it comes around after it, to be ID 2, and so on. So we can make a more semantic segmentation. We can also get more in-depth stuff like depth maps, optical flows, which is quite nice if we want to train a model on multimodal data. So it's not just RGB data, but we want to have some additional stuff there. And it's quite easy to also create more visuals and more visualizations by just implementing shaders and adding some simple rules in Unity. In Unreal, we don't have such a fully featured environment as in Unity, but we still have a lot of these very nice, very out-of-the-box solutions like Unreal GT and Unreal CV, as well as the Meta PUG that Meta, the company, has given away. The only problem with Unreal GT and Unreal CV are that they are kind of open projects that are created by, in one case, Unreal GT, I think it's one person. With Unreal CV, it's a couple of people. So the development of new features is a little bit slower, but you get the added benefit of open sourcedness. So if you want to change something in the code directly, you can easily do it. And of course, we have NVIDIA Omniverse Replicator. So that is NVIDIA's answer to creating these digital twin environments. It started as just an environment for robotics visualizations in, let's say, plants where you want, let's see, robot hands or movers to train them on synthetic data. But nowadays, they've branched to everything from open world synthetic data to visualizations for, let's say, home automation, for assistive robotics, for self-driving cars, and so on. It is very powerful. It's open source. It's free. It's not open source. It's C++ powered, which is also makes it a little bit faster than Unreal and Unity. But of course, while this is very specifically made for synthetic data, which is quite nice, the other two are very flexible and very open. So if you want to get your hands dirty, you can have even more options. And if you are a fan of Blender, because I have some colleagues that like to use Blender for generating their synthetic data, we have also from Google the Kubrick environment, which has the added benefit of full Python integration because of Blender's Python integration, where you can directly connect the synthetic data generation through Python to, let's say, PyTorch or TensorFlow, and then create your synthetic data and directly funnel it in to your models, which is quite nice that you can create videos and images. And the good thing is that they give Docker files for easy deployability. The bad thing is that because I am myself using a little bit more Windows than Linux, on Windows it's a little bit harder to get it running. And now I want to leave the last part of the presentation for some practical examples of my own research that might be interesting or might spark some debate or conversations. They are mostly from object detection and anomaly detection, but hopefully some people might see something that might be interesting for them. A little bit a background for this. So in 2021, I was part of a project that was Aalborg, the city of Aalborg, the municipality here, needed an automatic detection of people falling in the fjord from installed thermal cameras, because we had a lot of problems with people getting drunk and falling in the fjord. And of course, that was very problematic. The anomaly of people falling in water is incredibly rare. We had, from 3 years of data, we had maybe 3 or 4 cases on video, and they were very short and very murky. So there was not enough data for training anything. And we needed to create the data sets ourselves. But how? Our first attempt was to get some volunteers. As we can see here, this is a volunteer that we paid, we called the fire department, and we set up that they would jump in the fjord and we would film it. The problem was, of course, we needed the fire department, we needed a lifeguard on the spot, and permission from the police. It was very slow. We can do 1 or 2 people a day, and could be only done in a relatively warm and calm days, which in Denmark is by no means very easily obtainable, where even in the summer here is quite cold, and not realistic falling, because people were jumping. They would jump in a very specific way with their legs forward. They would try not to hit too close to the edge of the harbor because, of course, kind of self-preservation. So the data was not one-to-one with what a person would do if they fell. The next thing that we tried is to create a realistic, as much as we could, dummy and push it in the fjord. Here you can see me together with the dummy, and I try to do different ways of pushing it, kicking it, tumbling it, and so on. Still, we needed permission from the police, which is a very big problem. We needed a lot of preparation. We needed to warm up the dummy to make it visible in the thermal cameras. Every time the dummy fell in the water, it became colder, so we needed to, again, warm it up. We needed to change the clothes as well. We needed to put weights because even though the dummy was around 10 kilos, this is not a normal weight of a human. And you can even see here that even after putting a lot of weights and getting it up to 20-something kilos, we still could not get falls that were realistic. The dummy was much lighter and so on. And that's why we thought about ourselves, why not generate the synthetic data through Unity? And that's what we did. we took some of the realistic backgrounds that we already had. We segmented all the stuff that we wanted to be occluders. And then we created a lot of miximo characters that were walking around and falling. And we made videos out of that. The interesting part of this paper was that we had to create quite novel solution to create a thermal shader that we can apply to the dummies so it can much more nicely fit with the environment, and we would not end up with a gap between the synthetic and the real data. And we saw that even with very simple examples, as we can see here, of dummies that fall in different positions, we could get a very high, we could train a classifier that can say if a person is falling or not in the water with accuracy of around 94 to 95%. And while this was doing, we were creating this, we called it long-term thermal dataset, where we captured around 8 months of winter, spring, and summer data in 2021, where we had people, cars, and so on walking around. And we tried to annotate it with some humans, bicycles, motorcycles, vehicles. The big problem here, again, something that we saw that we need more synthetic data, was annotation of so much data, 8 months. So that was millions and millions of images, was extremely expensive because we needed to offload it to a company that was doing that. It took us 2 months of annotation and quite a lot of money to create the annotations. So one of the things that we wanted to take from that is to create variations using synthetic data generation, where we had some annotated data of people walking around, let's say, then get these human annotated pedestrians, run them through a variation autoencoder, and create a lot of variations between different ways that the person would be able to be represented, and then superimpose them on the images themselves. And we tried to do that, and we trained pedestrian detector, and we could see that even with a small amount of real data and a large amount of synthetic data, we can get much better results with a fraction of annotations only. And the next step would be to, of course, use diffusion models to even to generate even more variations of the captured image, the captured pedestrians. But one of the things that we saw from all of the previous experiments was that by this point, we were only using backgrounds that were kind of static, were kind of images. And then we were adding the synthetic humans on top of them, which meant that we could still get some models, if we train them only on synthetic data, that they would have problems with real data. So that's why we introduced this augmenting anomaly detection datasets with reactive synthetic elements, where we had initial pre-processing step where we could find the real pedestrians, let's say, where they are, and use them in our synthetic data as 3D objects. And if we add our synthetic humans here, dogs, or in our case, even stuff like bags, we could have them react to the real humans, move aside, be occluded. In the case here that we can add a synthetic bag to a person that's walking and the bag is being dropped and then another person kicks it. So we could get these kind of nice combination of real and synthetic data so we can bridge the gap between the two. Finally, something that is currently waiting on review is another thing that we figured out is that a lot of the data sets that we have online are very one note. In our case, a lot of them were very much in nice sunny weather or overcast weather with no changes in the environment. So we wanted to figure out if we can create a synthetic data augmentation on the real images where we can add stuff like particles for rain, for snow, for fog, and the particles would react, let's say, part of the particles can be occluded by the realistic people, and they can interact to some extent with the environment. So for example, here you can see the snowflakes that are touching the ground and kind of slowly getting more and more on the ground. So currently, we used Unreal again together with the built-in particle system and occlusion shaders to create this environment, together with some initial work with using YOLO V7 and DPT for depth estimation. One of the other things that we also figured out was that it was very not used. So we showed a lot of these things to deep learning researchers and computer vision researchers, and they found it very complicated and very confusing to use Unreal or Unity to do this synthetic data. And they asked us, okay, can you make an interface where I can just put an image and set up, and I want to have, let's say, some synthetic cars or some synthetic bicycles, and it's going to spit out, let's say, 100 different variational clips. I do not want to touch anything else. I just want to move some small things, and that would be it. So one of the things that we tried to do is a more user-centric approach, where we used another very famous scene called street scene, where we try to create this user-centric approach where a user can very easily click on different parts of the image and say, okay, these parts of the image are going to be occluders. You can say, okay, I want to have some cars that are with anomaly that they're stopped in an incorrect place, or we have some jailwalkers, or we have some bicyclists that are riding outside of the bicycle lane, and so on. And then we can output all the stuff that we showed here with segmentations, with annotations. And we saw that we can get a very nice testing with people that are using, that would want to use synthetic data. They managed to create the synthetic data using this data set in, let's say, 10 to 15 minutes with exactly the parameters that they wanted. We did a couple of iterations, and currently we're trying to clean it up. We have some groups working on this one. And just to switch it up a little bit, we were working also on detection of marine animal detection, where we wanted to have in brackish water to be able to track and detect fish. So one of the projects was here combining footage of real underwater scenes together with synthetic fish that can move in different positions. We can synthesize different occluders with bubbles, with different amounts of brackishness in the water, and so on. The fish can move semi-realistically. And we figured out that anomaly the fish trackers trained on the synthetic data can actually get up to 5 to 7% better accuracy because of the additional data and additional variation we can get. We are going to do the same thing also for fishing boats, where we have, let's say, a lot of caught fish, and we want to have a deep learning algorithm that measures the fish, counts the fish, figures out if there is a caught fish that's not the type that we want. Again, using Unity and using inverse kinematic fish and soft body fish, we can simulate a lot of the movement and a lot of the overlap that we see with real fish that are being caught on a conveyor. And finally, we are trying to do the same thing, but for training generative models. So one thing is that generative models have problems with realistic physical interactions. So for example, in our case would be train a generative model to generate full visual examples, because a lot of times if you train it just on images, the model would end up creating pool balls that do not hit each other in a video, but just kind of go into each other, or kind of bounce incorrectly, or don't even react, and so on. So one way that we try to mitigate this is by simulating a lot of these ball interactions, where we can have the nice annotated balls, but also get stuff like speed, kinetic energy, angle of hitting, angle of reflection, and so on. So this way we can have additional data that we can train a generative prototype. This is still in the prototype stage. We don't have any good results, sadly, to show, but I just wanted to add this as a nice teaser of stuff that we have. And I think that's about it. Hopefully I did not go overboard. This is my email and LinkedIn, and if you are interested or want to get in contact, I'll be more than happy. I really like talking to people and learning what they're doing. Yep.
Thank you so much. Very informative and insightful talk with many study cases, all very exciting. I think we are very close to finish, but we have some time for one question. If anybody have a question, anyone has a question?
Yes, can I ask a question?
Please go ahead.
Yes.
Yes. I can see that you have many of your synthetic data. How can you ensure they are as realistic as it is? I mean, since you don't have the ground truth sometimes when you generate the synthetic data, and also how do you validate them? Yes.
So that's a really good question. So, and that is a problem that a lot of researchers are having. How do we end up finding that it's good? The results are not just synthetic, and then you train on synthetic data, and then you end up with a useless model that cannot do anything with realistic data. So one of the ways that we try to mitigate that is by trying to mimic as much as possible the lighting conditions, trying to mimic as much as possible, combining for example, in the anomaly detection, we try to combine real humans and real backgrounds with the synthetic ones. So this way we can minimize the problem that we might end up with if we just generate, let's say, whole visuals that are synthetic in like some others have tried to do in Cinema 4D, for example, where we only see the synthetic humans with maybe realistic backgrounds that are not very much moving. So this way, we've seen that it's a little bit easier for the.
What about for animals? Like you have been using one of your project. You're saying using the elephant, the white monster, something. And
yes.
Also you use the fish, or what do you call the natural variation of these animals' movement will be quite different from how you can train. I mean, using your synthetic data.
Exactly. So for example, in the fish, one of the things that we ended up doing is implementing void movement to try to simulate as much as possible the variation with a lot of variations of, let's say, school size and movement size and interaction with the environment and so on. For the animals that I showed you with the monster thing, the project, I did not show it here, but the project is about trying to have animals in zoo environments. So the way that we try to do that is that we use as a starting point there real images of animals. So this way we get at least the texture is yeah. And then of course the problem is with the elephant movement. We try to mimic as much as possible movements of elephant. One thing that we would like to try to do is extract skeletonizations from real elephants and use that as initial visualizations. Let's say we have zebras and elephants and so on, but this is still kind of in early stages. We've only used it for humans because OpenPose, for example, is much easier to use for skeletonizations than some other stuff for animals.
So currently, is there any what you call the data set, open source data set for animals? I mean, I can see that there are a lot for human. I mean, those humanoid movement. What about for different type of animals? I believe that they are each different, have a different what you call movement and so on.
So from what we've looked into, for animals, you have like and most probably whoever is working with this kind of thing would know even better than me. But what we saw is that we can kind of separate them into captive animals and kind of the trap camera type of animal. And the sad part is that maybe the sad part for us is that captive animals is not that much that we have. We have a lot of chimpanzees and primates with much less data on other type of like pachyderms, like elephants and zebras and stuff like that. While with trap ones, we've mostly used the ones for Denmark, which is elk and boars more than anything, and birds. So there is gaps. There is absolute gaps that maybe synthetic data would be very useful there.
Sure, thank you. Very, very interesting talk from you. A lot of resources you have put in. Yes, thank you.
No worries.
Thank you so much. We have another question about the resolution of the resolution of the captured world in 3D and how it affects the result. For example, some critical details like a corner are missing from resource image, how that affects the generated 3D model. It would be great if you can answer this question.
That is a very good question, and that's something that we have a lot of problem with these kind of with the cameras, for example, in fish. Because in the fish cameras, we use a lot of these fisheye lenses, and you get a lot of these kind of effects, darkening effects. So what we saw is that if you do a synthetic data that does not have the same camera visuals, these kind of, like if you have blemishes, let's say, if you have these kind of JPEG artifacting from compression, and if you don't have these kind of, let's say, artifacting from imperfections in the lens, then the training would get really bad results. Actually, you get results that can end up with 20-30% worse, just because you are adding this gap between real and synthetic that's quite big. So a lot of care we've tried to do with approximating these camera effects. And the nice thing about nowadays the 3D game engines is that you get realistic cameras. So you get physical cameras. Both Unity and Unreal has physical cameras where you can change the ISO, you can change the shutter speed, you can change the aperture, you can add these kind of blemishes and post-processing that is actually quite nice and can help a lot.
Amazing, great. Thank you so much for answering the question. I hope it is answered to you satisfactory, the Celeste, because she's the one who asked the question. I would like to conclude this talk, and we would like to thank everyone who attended. And thank you, of course, for Evan for the brilliant talk. I'm very glad that we could have you today. It was great, and thank you so much for your time. Thank you, everyone, and I would like to conclude the meeting.
Yes.
Thank you. Bye-bye.
Bye-bye.